Alright guys, we're go, it looks like. So this is the second page. Yeah, second page of the notes here. It's a 1.2b. This is really problems, and it's really all problems that incorporate this thing called the segment addition postulate. And like I mentioned to you yesterday, you know what segments are, you know what addition is. This word postulate is just a rule for adding segment lengths. And essentially you're going to be adding and creating equations, usually addition equations. They could be subtraction equations. This could be a segment subtraction postulate. So on your paper, there's a little segment there. Just label 3 points. You know, you got one on the left, one on the right. Somewhere in between, not necessarily in the middle, is a third point. And like I said, somewhere in between, not necessarily the midpoint of those two. So you got A is on the left somewhere, C is on the right. The middle, the point that's not, sorry, the midpoint. The point that's between the other two, label that point B. And of course that's the key vocab word I'm looking for here. If B is between A and C, then you can write an equation. And we're going to be doing a lot of equation writing and solving here on these notes. So write an equation that relates the lengths of these three segments. This is going to be obvious for a lot of you. Some of you, it's going to be obvious after you see it. See if you can fill in those three blanks using lengths here. So an obvious answer might be, well, if you add this length, let's say this was 5 and this was 7, I could ask you, how long is the entire thing? You could say, duh, 5 plus 7 is 12, because you'd be adding AB plus the length of BC, and of course it would be equal to the entire thing. That's the little mini equation I'm looking for there. Here's my dimension lines on here. Length of AB plus the length of BC, of course, would add up and give me the entire length. If this whole thing was 20 and this was 6, you could certainly find BC. You know, if this was 20 and this was 6, you'd work backwards and subtract and get 14 for that. So this is sort of my little formula. You know, if I add up the two smaller ones, AB and BC, I get the entire thing. I get the distance from A to C. That is probably the most important postulate in terms of how much you use it. Use this thing like crazy this year. And use it in simple problems, use it in more complicated problems as well. So the whole front and back of this notes and the homework tonight is all about this postulate. You'll still see a few more problems about coordinates, but really this is the big one. Much more important than that ruler postulate from yesterday. So I'm really emphasizing this. This description here goes in the little box on your paper here. The segment addition postulate. Definitely something you want to highlight and know for every quiz and test from here going forward. So try example 1. Great time to pause, read through it on your own, and see if you can label this on your own. If you just copy what comes up on the YouTube video, you're not going to get a whole lot out of this. You're not going to learn much out of this. So the best thing you can do for yourself, read this, try to create your own drawing from your own reading, just like you would do on a test or a quiz or homework. You know, you create it on your own and then work from that. So like I said, good time to pause, and I'll show you what I've got here in a moment. I've got A between M and T, but you might not know where to put that in the beginning. You just know that M and T are somewhere on the outsides. And then you have T between H and A. So you've got H and A somewhere, and you might have to tinker with this drawing and erase it a few times. Then you might realize that Mr. Hess likes to write words in his problems, and this is one way you could label this. A is between M and T. Okay, I got the first part of the sentence. T is between H and A. That works. This whole thing could be flipped exactly backwards. H could be over here, T could be over here, A could be here, and M could be there. But it's going to say math either forwards or backwards if you do this correctly. Then I gave you some lengths. The distance from M to H, in other words this entire thing, is 16. The length of M to A, this piece, is equal to AT. This is not necessarily drawn to scale, but this length is equal to that length. And the last one, this little piece, is 4. And then there's 3 little parts on your paper I'm asking you to find. Find the length of MT, find the length of MA, and the length of AH. These are pretty simple. You know if the entire thing is 16, and I'm labeling that. On the bottom there I've got 16 labeled. I know the little one is 4. It's pretty obvious that the leftover piece, this one here, is 12. And of course we said these are equal, so they're both 6. From there it's pretty simple. I'm calling them X on there. Well, you know they're both, both of those values of X are the same, so they're both 6. So we got MT is 12, MA, of course we just said it was 6. And then AH is an overlap. From A all the way to H, you'd have to add the 4 and this 6 to get 10. Hopefully those 3 answers are pretty simple, make sense. So you'll see there's no algebra really here. I threw an X on here, but you didn't have to use any algebra for this. As we build up here, you're going to see more and more algebra. Again, you might want to try example 2 on your own, and then check back in the video here. I'm going to pause and go to a different section here. If I go more than 6 minutes on a video, sometimes I lose it, and it's unable to record it. So try this one on your own, come back to the second part to check your answers.